Okay, Assalamualaikum. My name is Muhammad Aiman bin Salali. Okay, I'm Department of Calculation. So, we choose for question 1, we choose 823 encoder. Okay, this is my calculation. So, we use for 823 encoder, we use 2 power of 8. So, the total is 256. Okay, for the expression, for y0 equal to d1 plus d3 plus d5 plus d7 times e. y1 equal to d2 plus d3 plus d6 plus d7 times e. y2 equal to d4 plus d5 plus d6 plus d7 and times e. Here is the equation.
Assalamualaikum, my name is Azran bin Azman and my number matrix is B122510-48. The circuit is an 823 encoder with an enable E control. The logic follows three equations. Y0 equals to D1 plus D3 plus D5 plus D7 times E. Y1 equals to D2 plus D3 plus D6 plus D7 times E, and Y2 D4 plus D5 plus D6 plus D7 times E. To build this, we use two stages. First, 4 inputs OR gates. Collect the data line D1 till D7 to determine the binary value. Second, 2 input AND gates act as a master switch. They only allow the signal to pass to the outputs Y0, Y1 and Y2. If the enable line is high, this design efficiently compresses 8 inputs into a 3-bit code while giving us total control over when the circuit is active.
So, Assalamualaikum and good evening. My name is Muhammad Azman Muhammad Azman, and today I will be presenting about the structural code for the 823 encoder. Okay, so on the right side is the design code, and on the left side is the test bench. Okay, so let's look into the design first. So the first thing, it has an 8-bit input representing our data lines. Secondly, it has an enable signal acting as an off and off switch. And thirdly, it has a 3-bit output for the final binary code. Okay, so moving on to the case statement. Okay, so the logic is simple. If enable is off, the output is forced to 0. If enable is on, then we will use a case statement. Okay, so it looks at which input bit is high and outputs the corresponding binary number. Okay, so for example, if bit 2 is high, then the output becomes 0, 1, 0. Okay, so moving on to the test bench on the left side. Okay, so we connect the design to our test signal and run a simulation. Okay, first we keep the enable off and toggles the input. The output should stay at 0. So this proves the off switch works. Okay, then for the second simulation, for the second case, we turn the enable on and then we trigger each bit one by one from 0 to 7. So here we expect to see the output count up in binary from 0 to 7. So this proves the encoding logic is correct. Okay, so in short, this code takes 8 input lines and compress them into a 3-bit binary code, and the test bench confirms that it handles both the active and disabled states correctly.
Hi, Assalamualaikum. Assalamualaikum. My name is Muhammad Ibrahim bin Usli. My metric number is BERN2413 Now I will explain about the simulation for question 1 and question 2. Question 1, we choose 8 to 3 encoder. First, input pattern validation. The waveform shows the 8-bit input in 7:0 being activated in one hot sequence 00000001 and 000010 and so on. This confirms that only one input line is high at any given time, which is the correct operating condition for an 8 to 3 encoder. Second, bitwise signal behavior. Individual input bit in 0 to 7 toggle sequentially, and which transition is clean without overlap. This demonstrates proper stimulus generation in test bench and ensure encoder output are not affected by multiple active input. 3. Output encoding accuracy. The output Y2:0 correctly reflects the binary position of active input. For example, when in 1 is high, the output is 001. When in 4 is high, the output becomes 100. This verifies the logical correctness of encoder design. 4. Enable signal functionality. When the enable signal is low, the output remains 000, regardless of input change. When enable is exerted high, the encoder responds normally. This confirms that the enable control is functioning as designed. Overall design verification. The waveform proof that the theoretical truth table, Boolean equation, and Verilog implementation are consistent. The simulation output fully match the expected encoder behavior, validating and the correctness of the circuit design. Hi, Assalamualaikum. My name is Muhammad Ibrahim bin Usli. My metric number is BERN2413
Okay, we go to the question 2. Okay, for the question 2, the question need us to design the circuit theoretical and verify the design through Verilog code simulation and reproduce the similar waveform of output M. Okay. So the problem statement, we get the formula from 2 power of 3 equals to 8. And this is our truth table. To show the truth table for question 2, we have input A, B, and C. So the output is M. During the table, you can get a K-map. This K-map, so the Boolean expression is M equal to A bar BC plus A BC bar.
This circuit implements the Boolean expression M equals to A bar BC plus A B bar C bar. Using three stages of logic, first we use a NOT gate to invert input A and a NAND gate to process input B and C. Next, these signals are fed into two AND gates. The top gate produces the term A bar B C, while the middle gate generates A, B bar, C bar. Finally, these two terms are combined through a two-input OR gate to produce the final output M.
Okay, so I would like to continue with question number 2 for the code structure. Okay, so we are looking at the Verilog projects that implements a specific digital logic equation and verifies it using a test bench. Okay, so on the right side, we have the actual hardware design, and on the left, we have the simulation environment. Okay, so let's start with the design safe, which is with a design module that we call it as a circuit Q2. Okay, so this module takes three input, which is A, B, and C, and produce one output, which is M. Okay, so the function of this circuit is defined by a Boolean equation found in the command, which is M is equal to A bar B C plus A B bar C bar. Okay, so this means that output M will turn on with only two specific situation, which is when A is equal to 0, B is equal to 1, and C is equal to 1, or when A is 1, B is 0, and C is 0. Okay, so the whole structure, the whole code implementation use a data flow modeling with the assigned keyword. As you can see, the A bar BC handles the first pulse. Meanwhile, the A, B bar, and C bar handles the second pulse. Okay, so the pipe symbol here represents the OR gate that combines these two equations, and any other combination of input will result the output M being 0. Okay, now we look into the test bench, which is we defined it as a TB circuit Q2. Okay, so we declare the register A, B, and C to act as our inputs, and then we used wire M to observe the output, just like connecting the output pin. Okay, then we take a look the simulation. Okay, so the simulation executes line by line. Okay, so the hashtag times represents the delay of 10 time units. Okay, so this allows the signal to stay stable for a moment before changing to the next test case. Okay, so we look into the first equation, which is the A equals to 0, B equals to 1, and C equals to 1. So based on our design equation, which is the A bar B C, this match our first condition. So here M become 1. Okay, so after that we look into the A equal to 1, B equal to 0, and C equals to 0. So this also was M equal to 1. Okay, so for the all other lines, the output will remain 0 because it doesn't meet the requirement. So here is the finish, means that it will stop the simulation. So in short, this script proves that our hardware logic correctly identifies the two specific binary patterns, which is a 011 and 100, and ignores everything else. Okay.
Now we proceed for question 2 simulation. Logic circuit timing and output amp analysis. First, input signal relationship A, B, C. The waveform shows input A, B, and C changing at different time intervals, ensuring all meaningful input combinations are tested. This variation verifies how the logic circuit responds to different conditions. Second, sequential input transition. The input change in controlled manner rather than simultaneously. This avoids race condition and allow accurate observation of how each input affects the output amp independently. Output amp logical response. Output amp change state only when specific combination of A, B, and C occur. This confirms that amp is governed by the intended Boolean logic rather than random transition. For timing consistency, the output amp transitions occur immediately after the relevant input change, indicating proper combinational logic behavior without unintended delay or glitch in the simulation. 5. Functional verification of design. The match relationship between input state and output amp verifies that the circuit logic is implemented correctly. The waveform confirms that the simulated behavior aligns with the theoretical logic expression used in the design. Thank you.